So in this session, we will be covering up RAG. RAG stands for Resource Allocation Graph. It gives a visual look how the resources and processes are executing each other by gathering some resources. Once process gets completed its execution, then you can release. That means process has to release all the resources voluntarily. So the RAG consists of G of V comma E. RAG consists of G comma E. G is equal to V comma E, where V is nothing but vertices, E is nothing but edges. Vertices are two varieties. Vertices are resource, vertices are process. And edges are two varieties. Edges are two varieties. One is process to resource, which is known as request edge. The other edge is resource to process. This is known as assigned edge. This is known as assigned edge. Okay. Then this is what is the meaning of G is equal to V comma E. So vertices represents the processes and resources. Edges are nothing but request edge and assignment edge. Whenever request edges come, the request edge might be transformed to assigned edge or waiting edge. If the resource is available, then it becomes a assigned edge. If resource is not available, then it becomes a request edge, becomes a waiting edge. And the other one is that once the resource is allocated to any kind of a process, soon after completion of the process execution, the resources will be deallocated. Therefore, that can be utilized to other processes. So deadlock existency with a single and multiple resource types. One is a single instance type of resource, the other one multiple instance resource type. Let me show you now. So there is a resource X has one instance only. There is a resource Y has one instance only. Process P1 and process P2. So this one already given to P1 because edge is coming from resource to process, which indicates that it is assignment. One copy available, that copy is given to P1. Therefore, this becomes busy now. This is a busy copy. And there is a RY, one copy is available, but this is also given to P2. Then this edge is known as a assignment edge. In this case, this particular copy becomes a busy copy. Now, that means only one copy only. Understand very carefully. I am drawing this example because of our single instance resource or single instance resource, single copy resource. Now, P1 is requesting for RY and P2 is requesting for RX. It is not possible because one copy is there. That copy is already distributed to RX and RY. Therefore, P1 by force is supposed to be under waiting. P2 by force is supposed to be under waiting. So, if it is a single instance type, if a RAG forms a cycle, then it indicates that it is a what? Deadlock. Blind, you can say answer. If it is a single instance type resource, and if there is a cycle form, then it is a what? Deadlock. But don't guarantee that in the case of multi instances. In multi instances, deadlock may occur, deadlock may not occur, even though it forms a cycle. Such kind of cycles are known as a phantom deadlocks. So looks that cycle is there, it forms a deadlock, but it never forms a deadlock. That concept is known as a phantom deadlocks. Let me write one more for multiple instances. Imagine multiple instance resources. Multiple instance resources. There is a resource Rx has got two copies. there is a resource Ry has got two copies and P1 and P2, two processes, and it is already given to P1 and this is already given to P2, and P1 is requesting for this and P2 is requesting for this. It looks a cycle, no, because this is freely available. This is freely available. So it looks like a cycle, but it is not a cycle because one copy is busy. Here also one copy is busy, but one copy is freely available. That is the meaning of multiple instances. Rx has two copies. One is already given to P1 and one more request has come from P2. Yes, of course, I can give it. I can give it. Then this is not there. We are not underweighting. In the same way, RY has got a one copy and P1 is requesting. So, okay, give it. What is the issue? Then there will not be any waiting edge. This is what's the meaning of multiple instances. Even though there is a cycle, we can't guarantee that there is a deadlock. To confirm that, you're supposed to use a banker's algorithm. If it is a single instances, blindly you can check it that it is a deadlock if there is any cycle. But multiple instances you have to be very careful that deadlock may happen, may not happen. There are two resources in this case. Y has got one resource only. This is P1 here. This is P2 here. This is already given to P1. This is already given to P2. And P2 is requesting for you. P2 is requesting for you. And this is available, right? So you can give it. And P1 is requesting for you. There is no copy. This is only one copy. This becomes busy. And this copy becomes busy. This is the free copy. This is a free copy. Even though there is a cycle form, I can give this copy to P2, then your cycle becomes broken. This is another example. And another example is there is a Rx and there is a Ry, and this is one copy is given to P1 and one copy is given to P2 and one copy is given to P3. Rx is having a two copies. That's the meaning of it. And P2 is requesting for Rx, but then no possibility. You're supposed to be under waiting because only one copy available. And P1 is requesting for Ry, not possible because already it is completely given. Two copies are given to two process. This becomes busy. There also becomes busy. So your request is supposed to be under what? Waiting. Then RAG forms cycle. RAG forms a cycle, but no, you can't guarantee that there is a deadlock because the multiple instances this example is talking all together. So how I can remove the deadlocks here? Imagine P3 P3 needs only one resource. P3 needs only one copy of Ry. That's it. After completion, one copy will be released. Completion after one copy is released. When this copy is released, then this copy becomes free now. When this copy becomes free, and that can be given to P1 now. That can be given to P1 now. So P1 assigned by Ry. That's it. P1 got executed. It is already hold Rx. Now it is already given Ry. So P1 successfully executed. Remove this. Then after that, P2 is get to be executed because soon after P1 is completed, it releases one copy of Ry. It releases one copy of Rx, and that Rx becomes a one copy free. Then I can give to P2. P2 happily execute. It also will be removed from the queue. So this is how you can remove the cycles in the RAG if there is any chance. That's why you can't take a risk even though there is a cycle occurred in the RAG. You can't confirm that there is a deadlock. So this problem can be eliminated guarantee that there is a deadlock or not decided by the banker's algorithm. So blindly you can't say. But if it is single instances, only one copy is available and a cycle occurred, blindly you can say that it is a what? Deadlock. So this example is talking about a RAG with a single instance. One copy R1 is assigned and R2 is assigned to P2 and P1 is waiting because there are no more instances freely available and P2 is under waiting. Then, as it is having a single instance resource type, I can say that it is a what? Deadlock. So this is also RAG with a single instance only. One copy, whom to whom given. R1 is given. R1 is given to P2. R2 is given to, sorry, R1 is given to P1. R2 is given to P2. And R1 is given to P3. Is it possible? Because you see that there are having a what? Two instances. So in this case, it is not a what? Single instance type. This becomes a what? Multiple instance. In this case, even though there is a cycle occurred, we can't guarantee confirm. So Pantham deadlock. A Pantham deadlock is incorrectly detected in a distributed system, even though no actual deadlock exists. So cycle necessarily, but not sufficient condition to say that it is a deadlock occurred. Even though there is a cycle, you can't give it. So this is mostly happening in which cases? Multiple instances.